Today we will study covalent bonds. So let's start. Let's imagine two hydrogen atoms, H reacting with H. We already know how the energy profile looks like. Now we should understand what is really happening there, how the bond is created. So you have a wave function 1s for one of the hydrogen, and you have the wave function 1s for the other hydrogen. It's supposed to be sphere. Now this wave function has a plus sign, and of course this wave function has also plus sign everywhere. Now when they come close to each other, what is happening? There are two possibilities that can happen. One of the possibilities is that these two orbitals overlap, and the other possibility is that the two orbitals overlap. You can ask me, what is the difference then? The difference is once they overlap with the plus sign, the other one they overlap with the minus sign. So we have two linear combinations. And the word linear combinations we already met before in this class when we were discussing that cosine of x can be represented as a linear combination of e to the ix plus e to the I minus ix. And of course you remember that in fact we had to put here 1/2 to get the equality. And we also said that the sign of x can be given as a linear combination of the same things, but with the minus sign. So here we had two linear combinations of two functions. So the two function 1 equal e to the ix, function 2 was equal e to the minus ix. And we are making two linear combinations of them, ones with the plus sign, ones with the minus sign, obtaining two new functions. Similar things happen here. We have the orbital 1s, which is a function, and we have another function 1s. And now we can put between them either the plus sign or the minus sign. What does it mean? If you put here minus sign, then this one can be written as a 1s minus 1s, but still it's not clear. But maybe it's more clear if I put this plus here and this minus here. Okay? So what it really means, first tells me change the sign of this wave function and then add them together. If I change the sign of this wave function, if I put that minus inside the wave function, then I get a wave function that is everywhere negative. You remember that the sign of the wave function doesn't matter in physics, because what matters is the square, so the sign is gone. So now we have two linear combinations, one with the plus sign, one with the minus sign. How they look like? In fact, after overlapping, these borders are gone, because now they belong to the same orbital, like that. And again, this border is not sharp anymore, like that. We get an orbital that looks something like this, with one nucleus here and the other one nucleus here. In the other case, when we have the plus and minus, you see that in this region, on this line, everything what is on this line will cancel and give 0. So the new orbital will look like that. as I said, everything on this line is 0. Again, this orbital has plus everywhere. This one has plus here and minus here. So we get two molecular orbitals. So, linear combination of two atomic orbitals gives me two molecular orbitals. Now, these orbitals had name. It was 1s. What about this orbital? Do they have names? Anybody knows? That's difficult, I know, but maybe somebody knows. Okay. These are called, well, since this is S and S, this is also S, but a Greek S. So the Greek letter S is written that way, and it's called sigma. So this is a sigma orbital. And this one is called sigma with a star here. We say sigma antibonding. Orbital. Good. We know the shape, but now we should understand the energy. So, before meeting, 1s energy, this is the energy scale. We have 1s hydrogen, and we have 1s of the other hydrogen, hydrogen number 2, and here is hydrogen number 1, and now they are meeting. My plotting is never perfect. They should be on the same line, of course. Okay, now it's better. Now they are meeting, and we have two new orbitals. What about the energy of the two new orbitals? This one is higher, and this one lower. The amount higher and lower is the same or not? No. Okay, which one is more lower? Which one is? Okay, they start from here. One goes up, one goes down. Is the amount down and amount up the same? No. Which one is more down or more up? Everybody can answer.
I'm not sure, but I think that
The up one? Antibonding. A bit lower. Okay. So the suggestion is one goes here and one goes here. Something like this, right? Okay. Now we should understand why one goes up, why goes down. Later we will understand how much they go up and down. Why one goes up, why one goes down in energy. I mean, it's easy to understand. Imagine that you have two small children, okay? And these two small children are closed in a small room. Let's say divided this class into half. One child is here, one child is there. They are alone, okay? And they have their own small territory to run. They are kind of happy. And in the one case, you remove the wall and both children can run in all the space. That's this orbital. And the other case, you keep the wall. So there is a door, of course. The electron can go from one part to another part, of course, because the wave function is the same wave function. It only has a zero value at some place. But you should understand that very close to the zero line, the probability of finding electron is rather small because the probability goes to zero. So in this region, the probability is rather small. Here, the probability is small only on the regions outside this line. So you see that in this case, the area or the space when the electron can be is smaller than in this case. So in this one, these two children are confined, they are squeezed into a smaller room. And the electron, to be in a smaller area, must travel faster, must have larger energy. So that's why one of them goes up, one of them goes down. So we have the sigma orbital here, and we have the sigma antibonding orbital here. So by the way, this one sometimes it's called sigma bonding orbital. Now, about the amount of going down and amount of going down. So in the first approximation, you should remember they are almost equal. But second approximation is they are not exactly equal. So you're right. But probably 99% they are equal. So if somebody remembers they are equal, it's okay. Good. We should also try to look at these two orbitals from this direction, from the direction of the line connecting both nuclei. So from this direction. If I make a plot of these two orbitals from this direction, what we get? Let's plot first this one. If I look from here, what I see is one s orbital of the first one, and just behind this one, maybe I use other color, just behind there is another orbital of the other one sticking out. And here is the two nuclei, one and behind there is a second. So I'm looking on this line and what I see is a perfect sphere. Spherical symmetry. And the reason to call this orbital sigma or S is this letter S for spherical symmetry. Okay. What happens if I see this one from this direction? Well, to be honest, what I see is the first one. Then there is a border between them that I don't see because it's behind. And then I see the other one. So this one has a plus sign, this one has a minus sign, and in this case this one has a plus sign and this one has also plus sign. In fact, this is the same, only there is a small valley between them that I don't see, and here there is a border, cross border. But they look the same. Both of them are spherical, both of them are round. That's why this one is also S sigma. But to put the information about the border between them, you get this star. We learned about the atomic orbitals. The atomic orbitals, they have nodal planes. They were angular nodal planes and they were radial nodal planes. This thing, this line, this zero thing, is nothing else like molecular nodal plane. In the case of atoms, we had radial and angular. Here it's difficult to define the same because there is no spherical symmetry for all the system. So there is no radial really. You just say molecular nodal plane. And the existence of the nodal plane that comes like that, or not existence like in this case, give you the difference between bonding and anti-bonding orbitals. Anti-bonding orbitals, they always have a plane between two nuclei. Bonding orbitals, they don't have a plane between two nuclei. Okay, let's go further. We analyzed what happens if one S reacts with one S. Let's go further and see what happens if the other orbitals are reacting with each other. So now we have one PZ reacting, and we know that it can be plus or minus again with one PZ. So let's put one nuclei here, another one nuclei here. We know that both of them are on the same axis, and let's call this axis Z. Now we are plotting PZ orbital. One PZ orbital will look like that, with the nodal plane here. Another one will look like that, with the nodal plane here. Sign, let's put here minus, here plus, minus, plus. I'm choosing plus on the positive side of the z-axis and minus on the negative side of the z-axis. Good. Now we make two linear combinations. Linear combination number 1, linear combination number 2. This linear combination with the plus sign. This linear combination with the minus sign. So, if you think what happens if I add this one and this one together, then this positive region and negative region overlap. So the orbital will look something like that. Plus, minus, plus, minus, plus. Okay, now it looks more or less similar story. The positive and negative are cancelling each other. Exactly on this line they are cancelling each other. This is the zero line. So we found a nodal plane. And the orbitals look more or less like that. And here is a nodal plane. Of course, it's difficult to write this nodal plane, but you understand that the nodal plane goes like that. It's all the plane. In the case of the minus sign, then the minus, I'm changing to the plus minus, and the minus enters the orbitals, and minus entering the orbitals, changing its sign. So minus minus becomes plus, and minus plus becomes minus. And now I see that the plus and plus overlap together. And I know what happens if the plus and plus overlap together. I get the border, no, the border is gone, and I get a small minimum here. Good, done. Now, of course, the one of the nuclei is here, another nuclei is here. So now I'm trying to look at this direction, at both of the orbitals. If I look at these orbitals from this direction, then I get exactly the same plots. One is the round part of this one. You remember that both these orbitals are in fact spherically symmetric, well, axially symmetric on the z-axis. So when I look from this direction, I just see a sphere. The sphere has a strange shape in this direction, but I don't see it. So what I see is a circle. Here is also a circle. So this also has spherical symmetry. So this is also sigma orbital. So S can give sigma, but P and P also can give sigma. It depends how they look from this direction. Now, this sigma has no nodal plane between atoms. So this is sigma bonding. This one has a nodal plane. This is sigma antibonding. So we know that for 2pz, the plot looks the same. Now, next question. This energy goes down. Compare S and P, make a sigma. Which energy is lower? Which energy splitting is lower? In the sigma case, you know that two orbitals go down, up like that. And for the p orbitals also they go up, down like that. Which difference is larger? Which one is smaller? For the s orbitals or the p orbitals? Which one is larger? One by one. S is larger.
P and a lot of S.
I think P, but I don't know. I didn't check it. But I think P, and I explain you why P. Okay? If you put together s orbital and a p orbital, the p orbital is larger. So, if you overlap two s orbitals, the overlap looks like that. There is only a small region or overlapping or reacting. But when you put together two p orbitals, the overlap is larger and the interaction is larger, and the energy should be separated more. Of course, nuclei are the same distance. This distance between nuclei are equilibrium, and this distance between is the same distance, are equilibrium. But I try to check it for the next class and then I tell you. Good, let's go further. We discussed what happens if 2pz react together. Now, let's see what happens if 2px react together. Two px, Again, we have the line connecting nuclei, one nuclei, second nuclei. We have the px orbital and another px orbital here. One of them has the plus sign on the positive x, the other one the same, of course. Now we make linear combination, the linear combination with plus and the linear combination with minus. The linear combination with plus looks more or less like that. Plus, plus, minus, minus. The linear combination with minus looks like that. Plus, minus, minus, plus. Now, the important part, this one merged together and this one merged together. Making such a shape with the nuclei located here. And in this case, the plus and minus make a nodal plane and plus and minus make a nodal plane. So here is the nodal plane and here is the nodal plane. And the linear combination looks like that, with the nuclei being here and here. Good. Something finally looks different. Now we should understand how these orbitals look from this direction. So we look along the line connecting nuclei. So we have one nuclei and behind is the other one. On the top there is this positive cone and down is the negative one. This is the first orbital. If I look from this direction, then I see the other part, this one, this part. And the other part looks more or less like that. And the other one, if I plot the other one, again the nuclei are here. The other one is also a plus sign and minus sign, but the part that is behind will have different sign. This one will have plus, and this one minus, and this one will have plus. Okay, so when I look from this direction, this is not anymore spherical. You see that to change sign, I have to rotate 180 degrees. And to change sign to the beginning one, I have to rotate 360 degrees. This is polarized. And from the first letter of the word polarized, P, I have the name of these orbitals. Again, Greek letters, P. This, for atoms, you have normal letters P. For molecule, you have Greek letter P. Or pi, sorry. Now, with this pi, which one is bonding? Which one is anti-bonding? Like always, the anti-bonding has a plane, nodal plane. So you see that the nodal plane is here. This is the anti-bonding pi orbital. What about the strength of this pi bond? You know that the pi bonds are weaker than sigma bonds already from high school, but here you have the reason why. If you plot together the pz orbital and px orbital, and you see that the overlapping in a bond between 2pz is very large, but between 2px the overlapping is through space kind of. So very weak overlap. So usually the splitting for the pi bonds is very small. It's around here for the 2px. 2px. Now you should understand also that if I don't use px but I use py, the situation looks exactly the same, just in different plane. So I have 2px, 2py here, 2px and 2py, and the picture in the middle looks something like that. Two px, 2py, 2pz. 2px, 2py, 2pz. pz and pz makes a sigma bond, low in energy, out of 2pz. pz and pz make a sigma bond, anti-bonding. Then, next part, px and py make a pi bond. Px make a pi bond and py makes a pi bond. Px make a pi antibonding, py makes pi antibonding. So you have here pi and pi antibonding. So this is the energy diagram for chemical bonds originating from 2p orbitals. So we learned already sigma bonds and pi bonds, and you know sigma bonds and pi bonds from the high school. Is it everything? No, what is else? Delta, yes, good. Delta bond is the next one. Is it everything? And the answer is again no. There is no limit. It goes to infinity. But the nature, in mathematics, it goes to infinity. In physics, the highest bond that I've seen in a molecule is delta bond. But you can go higher. Let's write a delta bond. Now, first, you should understand first that if you have dz square plus another dz square, then you are getting sigma and sigma antibonding. It is a boring situation. If you have dxz reacting with dxz, or if you have dyz reacting with dyz, you are getting from this one, so there is plus and minus, here was also plus and minus, you are getting from this one pi and pi antibonding orbitals. So the only interesting situation happens when you take two dxy orbitals plus dxy. How to plot this one? Of course you have to take dxy orbital. Dxy orbital is in this plane and another one is in this plane. So let's plot it. One part sticky, no, not good. One part sticking to us, the other one going down. Maybe I try. If I don't succeed for 3 times, you have to imagine. Okay, now one of the orbitals has a cone here, another one there, and this is with the plus sign. The other two cones are coming, one of them is here, the minus sign, and another one is here with the minus sign. Now the other atom, again, plus, plus, minus, minus. Okay, when they come together with the plus sign, the plus and plus overlaps. There is a bond between these two. There is a bond between this. Now this orange also make a bond, and this orange also make a bond. So you see that if I look from this direction, and I put one nucleus here, then I will see 4 cones. With the plus sign, minus sign, plus sign, minus sign. So this orbital, to change sign, you have to rotate by 90 degrees. If you rotate it by 90 degrees, plus, minus comes to plus, and the orbital changes sign. This type of orbital that looks from this direction like that is called delta orbital. And now the delta bonding or anti-bonding comes from the fact if the plus interacts with plus, or I'm putting a minus sign between them, and after putting minus sign, of course, the sign here is everywhere changed, and I'm getting here minus, plus, minus, plus. And from this combination, this minus already entered. From this combination, I'm getting the anti-bonding orbital. So this is delta bonding in delta anti-bonding. And if you think about that for a moment longer, you also find that dx squared minus y squared plus dx squared minus y squared make the same linear combination of delta bonds. Delta bonds are very, very weak, extremely weak. If I plot them here, probably the delta would be somewhere here. Again, I can do this because the plot will look virtually the same. So I have the d orbitals. There is 5 of them. And I need at least 3 d orbitals for hydrogen. And I know that dz squared gives me sigma, dxz, dyz gives me pi, and the delta ones will be given by the dx squared. This is the delta, and this is the delta antibonding. What happens further? If you go to the f orbitals, there is one f orbital that doesn't look like that, but looks like that. Plus, minus, plus, minus. If you put another orbital exactly like the same, this direction, then the overlapping of these two will give you something what is called f orbital. In Greek letter is phi, or phi, depending. So there will be phi orbital. Then if you go to the g orbitals, you would have 8 arms. And that would be h. What is h in Greek letters? I don't know. Maybe chi, I believe. But I never seen even or heard about this. The phi orbitals, they are pretty often used in quantum chemistry in discussion. Okay. Now one small addendum. What happens if the 1s orbital reacts with 2pz? Is it possible? So now the answer is, if both of the orbitals from this direction look the same, the reaction is possible. If you look from this direction and both orbitals look different, the reaction is not possible. So if you look at this direction, at this one, you of course see a sphere. If you look from this direction at this one, you of course see a sphere. So it's okay. You can make a bond. You again have the plus and minus linear combination. And what you are getting is, okay, this is plus everywhere. This is minus plus. So with the plus linear combination, you are getting something like that. Sphere overlapping with this one. The other one, you are getting sphere overlapping with this one. In this case, the plus sign and minus sign came together, so you get a nodal plane. And the nodal plane looks a bit funny here. Something like this. And in this case, the sign is plus, plus, minus, so after overlapping, you get one big orbital. More or less look like that. And of course, this is sigma antibonding, and this is sigma bonding. Let's go further. What happens if 1s reacts with 3dz square? The same story. The only difference here would be the circle, and well, no, there would be a difference for the minus sign and for the plus sign. So for the plus sign, everything looks more or less like that, with the minus here. And with the minus sign, you get this one, of course, minus, and here the sign will be plus on this one. And again, sigma, sigma antibonding. No big difference. What happens if we try to connect this one with px? Then we have the problem that I discussed. S from this direction looks like a circle, but px from this direction looks polarized. It's not circle, it has the plus minus sign. So they have different sign. If you try to connect them anyway, if you try, what would happen? One second. Now it's minus, plus, plus. You see that the plus and plus, this region would combine together, giving something larger. And the minus and plus would also combine together, giving a nodal plane. Good. And this one will look virtually identical, but would be at the bottom. Of course, I can stop the explanation here saying that this one looks ugly and nature doesn't like it, but the real reason why this is never happening, because the plus correction from here cancels the negative correction from here. So the energy gain is zero. So this one is not making a bond. Similarly here, the positive energy gain is cancelled by the negative energy gain by these interactions. So this is just to remember, this never happens in nature, even if you can plot it. Good. But of course, there is no problem to imagine a pi bond between 3dxz orbital and px orbital. 3dz looks like that, with the where is plus? Plus, minus, plus, minus. And you see that after making a bond with the plus minus sign, this plus would merge, this minus would merge, and finally they would give a pi bond and the pi antibonding. You can imagine this, how this one looks from this direction. You will see that there one part is positive, one part is negative. Okay, this is everything what you have to know about making bonds. The really important part is to remember this plot. So now we should understand what happens, we know how the atomic energy level looks like. We said that everything starts from 1s, then we have 2s, a bit higher is 2p, then is 3s, a bit higher is 3p, a bit higher is 3d, then we have 4s, which is lower than this, 4p and 4d, and somewhere there 4f, and so on and so on. These are atomic energy levels that you know very well. Now what about molecular energy levels? To be honest with you, not big difference. I'm taking one S level from one atom, one S level from another atom. I'm coming to the same region and I'm going down and I'm going up, putting sigma and sigma antibonding. Now I'm coming to 2s. 2s again should be here, but I have the splitting of the sigma and sigma antibonding. This is originating from 1s. This is originating from 1s. This is originating from 2s. And this is also from 2s. Further, I have the 2p orbitals. The 2p orbitals, the original level is a bit higher than s, so let's say here. Then I have the splitting to sigma, and I have a splitting to the pi. And I have sigma, pi, pi antibonding, sigma antibonding. And of course all of this is originating from TP. 2p, 2p, 2p. Next one is 3s. 3s gives me around here, gives me 3s, 3s sigma, sigma antibonding from 3s. And so on and so on and so on and so on. You see that the levels here are very close. So the patterns start to overlap. So that it's very complicated. But the important part is that in an atom you have the level which is one time degenerated. It means it can have maximum 2 electrons, 3 times degenerated level, 5 times degenerated, 7 times degenerated. In this case, in the case of the molecule, the highest degeneration is 2 for the pi orbitals and delta orbitals. Good. Let's go further. How I put electrons there? Well, if this is hydrogen molecule, H2, I have 2 electrons, one from one hydrogen, another one from another hydrogen. So I have 2 electrons, I put them at the lowest level. So the electronic configuration from hydrogen 2 is sigma 1s 2 electrons. What is the electronic configuration for, let's say, lithium-2? Lithium-2 has how many electrons? 6 electrons. So I'm putting 2 here, 2 here, 2 are left. Where they come? Well, the lowest level is here. So the configuration is 1s anti-bonding, 2 electrons, sigma 2s, 2 electrons. We'll come back to these configurations a bit later, but you see that this is nothing really different from atoms. Kind of similar thinking. Okay. Let's go further to something what is called hybridization. Generally, hybrid is a mixture, usually of 2 animals. So something strange, something what shouldn't be made but was made, hybrid. So now you know there is a name for the hybrid cars that use both ethanol and gasoline, or electricity and gasoline. It means using both, having 2 functions. So hybridization is a similar thing. In atoms, S, P, D, F, orbitals have different symmetry. But if you go to molecules, you see that S, PZ, dz square, in fact fz cube and so on, have sigma symmetry. And to be honest, I should add here linear molecules. Linear molecules. Then we know that px, py, dxz, dyz, fyz square, fxz square have pi symmetry. You also know that the other one, which is dxy, dx square minus y square, and I don't remember the further, have delta symmetry. So in atoms, I couldn't mix S and P because they have different symmetry. But in a molecule, I can mix S and PZ because they belong to the same symmetry. They look the same from the axial direction. So I can make a linear combination of these in one single atom before going to molecule. Turns out that if you don't have linear molecules, general molecule, then S, P, D, F have the same symmetry. And I can mix everything with everything. This mixing makes linear combination in mathematical sense. Now I try to explain what is the good point of mixing. Let's take a linear molecule with the s orbital and pz orbital. Now, for one atom, I can make two linear combinations. Inside one atom, remember, this is a difference. Inside one atom, the linear combination with the plus sign and linear combination with the minus sign. So in the first case, when I have plus sign here, minus here, plus sign here, the linear combination with the plus sign will look something like that. In the other case, when I have the minus sign, the linear combination would look something like this. With the minus, that would be minus here. So again, I have two linear combinations. Both are sigma type. And now one linear combination has long tail this direction, one has a long tail this direction. So this orbital can make a bond to this side, this orbital can make bond to the other side. And this is exactly how the bond is made in linear molecules. So let's take some linear molecule. Hydrogen 2 would be fine. No, we don't have p orbitals. Lithium 3, yes. So in lithium 2, in fact, I was lying to you a moment ago, writing a simple plot. In lithium, before the bond happens, first we have the hybridization. And then the sp and sp overlap together into the. So first in lithium we have this hybridization of s and p, and then this big s and p reacts together with the plus sign like that to make a bond. So probably the bond in lithium looks something like that. Okay, this hybridization is called sp hybridization, and the reason for this is that you have one function s and one function p. And this hybridization happens only for the linear molecules, for the kind of chain molecules. Let's go further. If you have flat molecules, flat molecules means molecules in a plane, then very often hybridization is a hybridization of one s and two p. Now, in this case, I have two orbitals, gave me two linear combinations. Here I have three orbitals, gives me three linear combinations. And here it was just simply plus, minus. Here is more than plus and minus. There are some coefficients. I don't remember what are the coefficients, but you get three orbitals. The orbitals look like that. One of them is like that. Other one looks like that. And one more looks like that.